Okay everyone, so today we're going to talk about gravitational fields, but just a slight admission of something I got a little bit wrong, which is when I wrote that Newton's law of gravity is this equation here. What I missed out on was the direction, and that direction has to be shown by there being a minus sign here. There's a few reasons why the negative sign is in existence, but the easiest one to think of is that what we have when we think about say electric fields, so you've got a positive and a negative. When you use Coulomb's law, you end up with Coulomb's law is K Q1 Q2 over R squared, which looks very, very similar. And if they are opposite, you'll end up with this coming out as being a negative number, because if one of these is positive and then one of these is negative, and that's the case for it being attractive. So negative numbers, when you get these things, must be attractive forces. And what happens is, in this case, what this means is that we need there to be a negative number actually in the equation itself, because we don't have, at least as far as anyone knows at the moment, we don't have negative masses, because gravity is always an attractive force. So yeah, there is a minus sign there. For which I apologise. I often forget about it on the basis that it's, when you deal with gravity, you always know it's an attractive force, so you can always work out the directions, but formally there should always be a negative sign there. Now, gravitational fields is the thing that we're going to talk about, and we're going to talk about the what we need to talk about when we think about things being called gravitational field strength, which since you first came across it in year 9 has always been G, a little g, and the units of it, G is always has units of newtons per kilogram. So the gravitational field strength is a measure, okay, of the force exerted per unit mass in that, on the object placed in a field. So it is, so gravitational field strength is so the force per unit mass on an object in a gravitational field. Okay, which is similar again to electric field strength. So many of the things are the same. So what we get is that G is therefore defined as the force divided by the mass. Which, when you think about, when you're dealing with weight and on the Earth, that force, if that force is W for weight, then that's how you get the weight is mass times gravity and relationship. But if we're going to think about it in terms of Newton's laws, we could actually put Newton's law in there, and so we'll get G is equal to minus G m1 m2 over r squared divided by the mass of the object, which is, I'm going to say that's m2 because that's by convention the smaller object, over m2. They will cancel and we get minus G over r squared. And that is the gravitational field strength when you are a distance r away from an object. And that is great for us because we can do a quick test and we say, okay, does it agree with what we expect, which is the 9.81, and we can put our numbers in, where G is therefore equal to 6.67 times 10 to the minus 11. The mass of the Earth is 6 times 10 to the 24 24, and the radius of the Earth, I'm rounding quite a bit here, 6,400 squared. That's the radius of the Earth, give or take, you know, a few hundred kilometers. Minus 11 times 16 to 24. And what we get is 9.77. And as we discussed, that G is a variance a little bit. It's different from 9.81 because, you know, these are estimates. It's not exactly this. And also 9.81 isn't averaged out over the course of the Earth, which has to account for the centripetal accelerations as well. But that is G on the surface of the Earth. And it's pretty much there wherever you are on the surface of the Earth. As we saw, you can go up to Everest. The force on somebody at the top of Everest doesn't really change very much. So that is nice. So what we have at the surface of the Earth, we have pretty much a constant G field. So if we looked at the surface of the Earth, what we would have is any object that's in it would have a series of gravitational field lines, and they'd point downwards, and they would be parallel. So we can represent the strength of gravity, okay, the gravitational field strength, by having gravitational field lines. They point downwards because fundamentally, hopefully you're aware, if you drop any object, then if you drop it, it's just going to move downwards. So I guess to there. So what we can show is we've got a gravitational field strength. Now, if we zoom out, we go to very large things, what we'll have is we'll get a radial thing of our strength of gravity. So if we go far enough away from the surface of the Earth, we'll end up with a radial field. Oh God, it looks like sunbeams. So as you go out, it's going to decrease radially because obviously we've got this factor of r squared in there. So we're going to go, so G is going to decrease. So we can, let's consider just an example. Let's go to the moon. The moon is in the Earth's gravitational field. It is 380,000 kilometers away. So what's the strength of gravity if you're at the moon? So if you go to the moon's orbital distance and you just sort of, float there, what is the pull of gravity on you from the Earth? And we can work that out. So G, at the moon will equal the ratio of the Earth moon squared, so we get 6.67 times 10 to the minus 11 times 6 times 10 to the 24 all over 384,000 kilometers squared. So we'll work that out. And working that out, I get a value of 0.003 newtons per kilogram. So if you go and stand, if you go to an orbital distance, the same distance away as the Earth, sorry, the Moon is, you are still not weightless, but you're getting a lot closer to it. You're getting very, 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 it's quite amazing. So, an 80 kilogram person has a weight on them of about 0.2 newtons. So that is the sort of like the size that we kind of get. So what this means is that as we go away from sort of the Earth, we get is if we go sort of away from the Earth, or away from any planet really, what will happen is that if this is the force of gravity and this is our radius, what we get is a curve that's doing this. Okay, so it's a 1 over r squared sort of curve. So as we get further and further away, we end up having a smaller and smaller gravitational field due to that object. Now, the question then becomes, well, what is going on here? Okay, so this example, this would be the radius of the Earth, or radius of the planet. Okay, and there, what you have is a value of g on the surface. Question becomes, what is happening here? Now, for an object which is a point mass, so if you imagine, say, something like an electron, hasn't got a size, hasn't got a volume, then what you'll end up with is, you just have, for a point gravitational mass, it's easy. You just have gravitational fields that do that. A bit like when you deal with the electric fields coming out of protons or electrons, you just have them as a point and they go into them because it's easy enough to assign them as being this kind of point-like structure. But it's like the Earth doesn't have a point-like structure. And one of the things you might work out, well, these lines can't just go through the Earth. They can't just go through like this, because what that would mean is that by the time you got to the centre of the Earth, the force of gravity would be exceptionally high. And that doesn't make any sense, because if you go underground, well, there's less mass beneath you that's going to keep you on that path. So you're going to end up not with the same sort of thing. So let's think about what happens inside a planet. And we're going to make it easy. We're going to do a planet of uniform density. So we're going to take the planet to be a uniform density, which we know it isn't. We know the Earth isn't uniform density the whole way through. But it's okay, because you could just sit there and go like, well, okay, I just mean I'd have to deal with the Earth in a series of concurrent spheres of different densities. So there's the central core layer of the Earth has a certain density, then you've got the next layer and the next layer. So you can still do it, means you have to just do the calculation loads and loads and loads more times. So let's imagine we've got the Earth and we've got the centre, and we're going to go out to the radius of the Earth. And we're going to assume that the Earth has a uniform density. So what we know is that the mass of the Earth is equal to 4/3 pi r e cubed rho. That's the mass of the Earth. And what we can just simply do is say, well, okay, well, what happens if we just go to, let's say we go to this point here. So we in fact just go a distance r along. what we can get there is say that the the mass at a distance r is 4/3 pi r cubed times rho, and we can then put that into the equation for gravitational field strength. G is equal to minus g m over r squared, and so what we get is minus g over r squared times by 4/3 pi r cubed rho. And what's nice is that these things will cancel. That cancels with that, and we're just left with minus g 4/3 rho r. And this becomes a nice equation for inside the Earth, or inside any object of a constant density. So in a constant density, inside a planet, the gravitational field strength will increase linearly as you go out from the centre. So we get an increase as we move from the centre. So if we were to go back to this graph, what happens in there? Well, it will happen like this. And that is how we can deal with gravitational fields both inside and outside a planet. So this is inside and this is outside. And which makes sense, because if you were to imagine that you were sat at the very centre of the Earth, not sort of worried about the fact that it's exceptionally hot and you've melted, then you should be able to sit there and go, well, I shouldn't have any gravitational field strength due to the Earth, because I should be being pulled equally in every single direction by the mass that's all around me. I should be held at a kind of stability point based on the fact that the gravitational field strength is the same in both directions. And so that's kind of what we can do. It's very similar to just using Newton's law itself. But it is an equation that allows us to deal with what happens when we start going off the Earth. And that essentially is... Actually, turns out it wasn't quite done yet. So just a quick sort of touching base on the opposite of what would we do when there's a lot of objects to worry about. Well, force is a vector. So ultimately, you just treat things like vectors. You can add and subtract them in the same way you do with like Newton's laws on the Earth when you're dealing with friction and stuff. It's just the same idea. You just have to be a bit more clever about them. So let's say you've got some different objects. So let's say we've got planet A and we've got planet B. And in between them, we have a sort of a rocket or whatever, and it's at some distance between them. Now, as long as if we're being completely what we get on here is, let's call this C. What we'll get here is we'll get a force that way on A, which is the force on A due to planet B. We'll also get a force on A due to the object C. B will get a force on B due to object A. We'll also get a force on B due to object C. And for object C, which is our travelling thing in the middle, our little travelling companion, it's going to have a force on C due to object B, and it's going to have a force that way, force on C due to A. Now, if we work on an assumption that the mass of C is very small compared to the other two, then that kind of means that in many respects this force and this force might essentially become negligible. Like, for example, if A is the Earth and B is Jupiter and C is a small rocket with one slightly confused person in it who's thinking it's a bad idea, then it's not going to have a huge gravitational impact. But it will. It does have a gravitational impact. So, if you're being if it's 3 planetary bodies, you have to start worrying about all of them. But you just treat them as in their vector additions. If you start worrying about things at an angle, so you've got if you've suddenly got a thing, you've got A, C, and B, you've got 3 planets sort of up this sort of way, then you have to start dealing with them in 3 dimensions and deal with the forces on them. So, if you think about this object here, you've got a force that way and you've got a force that way. Highest likelihood is that if they gave you this, you'd end up with it being a right angled triangle. So these would be right angles in order to make the maths easier. But you'd get so that's the force towards B, the force towards A, and you'd end up with the ability to say, oh, okay, right, I can treat these like vectors, stick that one there, and get a resultant vector. Which is my resultant. The thing is that what happens with all of these and why it becomes more complicated is not essentially this instantaneous static position, because you can solve it for a static position. Where it becomes more complicated and where it goes beyond the scope of an A-level course is then asking, okay, well, as this thing moves, so as this thing starts to travel, if let's say it starts accelerating that way because of the forces, well, suddenly you're going to affect all the other forces. You're going to affect the size of force B and you're going to affect the size of force A because you're now changing the distance between them. And that is where you have to start using calculus. So although you can sort of solve an instantaneous problem, it becomes complicated quite quickly because you have to keep resolving it, or you have to approach things in a slightly more clever way. So there is this idea of what to do when you have more objects. The other thing to consider is what you do. Last thing to consider is if you're doing this journey, and let's say you're in this rocket ship, and you're moving from A to B. Now, at a certain point, there is a point at which the gravitational pull, the field due to A, and the gravitational field due to B are going to cancel out. There would be a point at which you should be in a sort of like a net neutral thing, where the forces, if you drew them as forces, you'd have a force that way. I would, at least if I could hit the right pen. You've got a force that way and a force that way, and they're the same. And what that means is that you are in a place at that instant there, that is where G is equal to 0. And the formal name for that is called a Lagrange point, I believe. And there's a few different ones all around different objects based on what's in their local area. And it's where you can go to this little point of stability that if you sit, you won't move towards either of these objects. Hard to find because obviously all these things are in motion as well. But in order to draw that, if we were to map sort of what happens to, if we were to draw our sort of our strength of G with R, what we need to do here is actually have a sort of crossover point. So we'd have the point due to this, and then you'd have something which would start to climb up by the time you hit the surface of this planet. And that's the surface of that planet. But much like the forces, if you want to know, so that would be the 0 point essentially. But much like the forces, you can always find this idea of if you want to know what the overall gravitational field strength at any point. Remember, it's an acceleration, it's a vector. You can always add and subtract them like vectors. So, if dealing with multiple objects, or multiple bodies, the forces or gravitational field strength can be found through the vector sum.